Thank you, Connor, for the introduction. And thank you all members of the audience for dedicating time to watch this presentation. If you have any questions during the presentation, just go ahead and post them. And what we will do is just answer them at the end. I am a minimalist when it comes to presentations, and also recognizing that we have a diverse audience with different backgrounds and different levels of experience. So we're going to keep the technical aspect to a minimum while still giving you enough information that will help you make decisions in your next project and in future projects as well. So without further ado, let's just move on to the presentation. We're going to talk about selecting and designing magnetic components for power supplies. And we are going to start by talking about how Premier Magnetics can help you in your designs. Premier Magnetics not only strives to servicing the customers, but to building relationships. And then later in the presentation, we're going to talk about the technical aspects on how increasing the switching frequency of a power supply will affect a magnetic component. Then we're going to conclude by going over an example to have a better grasp on that concept. Premier Magnetics always tries to meet the customer needs, whether it'll be meeting a certain cost, performance, or size. And what we will try to do is fit your needs based on our vast catalog. So we have a wide array of components in our catalog. However, we also understand that sometimes we have to tailor a design to meet your particular needs, whether it is meeting a target price or meeting an efficiency level, or just complying with certain regulations, as well as feeding the component in a very tight space. But you may also want to change the mounting options, so going to a surface mount, etc. We can help you in every aspect of the power supply. Starting with the input filter, we can help you with a common mode choke or an inductor, as well as the power factor correction stage, where we can give you a component that will meet all your needs. In the same way, we can help you with a transformer or an inductor for the power stage, as well as the output filter inductor, where we can help you with different components if you will prefer to test. Now, also, we can help you with the control stage. So many of our customers will utilize a transformer as a gate drive to control the switches in a motor application. We recognize how the industry is always trying to reach higher levels of efficiency. They want smaller components and, of course, lower cost. And as engineers, we would love to see the components in our systems shrink as much as possible while keeping the same level of performance. And the power electronics industry has been adopting gallium nitride and silicon carbide technologies that hopefully will help us reach those goals. But let's have a discussion on how changing the switching frequency will actually affect either the transformer or the inductor in the application. For this, let's start by defining what the flux density is. So here, defined by beta, the magnetic flux density, we can think of it as the magnetic stress that either a transformer or an inductor sees during the application. Now, the magnetic flux density is defined by the flux linkage, here defined by lambda, which is based on the operating conditions of the component, whether it is the inductance and the operating current, or the voltage level and how long you apply that signal for. Now, in the denominator, we have AE, which is the cross-sectional area of the core, as well as the turns. And if we simplify this equation, we can think of the whole denominator as the size of the component. So The flux density is based on the operating conditions of the part as well as the size. So if we start off with a particular size that defines the flux density, and then we were to increase the flux density of the component while keeping all other aspects the same, such as power level, switching frequency, and everything else, including the size, except the magnetic designer will change the internal structure of the component. What you will see with a higher flux density is that the core loss will increase, but the windings are going to be more efficient. Now, another way of looking at this is that if we have a particular size, and if we want to increase the flux density, we can actually reduce the size of the component. And this is exactly what you will see when, for instance, a customer receives a sample from Premier Magnetics, and the customer says, hey, this is great. The part is meeting all the requirements in my system. I actually see that the part is not getting hot at all, and I don't plan to change the operating conditions. Can we make the part smaller? And this is exactly what a magnetic designer will do. They will change the size and internal structure, therefore increasing the flux density. But of course, we have to think that just as in the previous example where we kept the same size, the core will get hotter and the windings will be more efficient. The difference is that here, since we're reducing the size of the component, we are going to be dealing with a more power dense component. Therefore, we're gonna have the benefits of more efficient windings, and we may end up with a hotter component. But somebody will say, wait, I know that the frequency is inversely proportional to the flux density. So why don't I just increase my switching frequency, therefore decreasing my flux density, and then I can reduce my size without affecting the performance? Or the same person could say, well, if I do the same thing, increasing my frequency, but keep the same size of the component, then I should see a more efficient part because the flux density is lower. And that's a great train of thought. But when the part is plugged into the system at a higher switching frequency, what we may see is actually the part getting hotter. And to be able to understand this, let's just delve deeper into the technical aspect, but going through an example. And for this, let's start off with the core loss versus flux density. This graph is a very genetic graph based on actual materials in the industry. And for this, let's start with an application. So a typical application for a power transformer, let's say we are designing that at 150 milliteslas for the losses. And let's assume that we are working with a system that is starting to operate at 100 kilohertz. So then we trace this, and if we assume for simplicity purposes that the volume of the core is 1 centimeter cube, then our core losses are going to be 200 milliwatts. So the person says, okay, so I have 200 milliwatts. I am operating at 100 kilohertz. What if I just go to 500 kilohertz? Then, since I am increasing my switching frequency 5 times, then I should see my flux density be reduced by 5 times. So I should get 30 milliteslas at 500 kilohertz. My core losses will drop to 80 milliwatts, therefore having a more efficient component. And at first glance, this is a eureka moment. We will say, oh, this is great. This is going to solve all my problems. But let's go back to the flux density formula. So remember that we actually simplified the formula by declaring the whole denominator as the size. Now, let's remember that that also includes the turns. And so when we think about the whole denominator in this case, in this scenario, we can also think of the denominator as the overall construction of the part. So the overall construction meaning the size as well as the internal structure of the windings. So the way to think about it is we have all the windings, and since in our industry Well, we are constantly asked to deliver a smaller and a smaller component. Most of the times, the turns and the windings are going to be crammed into that space that we have available. So in this example, let's say that in that transformer, we have the following scenario where the red circles represent the primary winding, the yellow stripe represents the tape between the windings, and the blue circles represent the secondary winding. Now, what happens when we increase the switching frequency from 100 kilohertz to 500 kilohertz? Then what's going to happen is that the parasitic effects on the component are going to be more evident, be it the interwinding capacitance. So the capacitance between windings is going to be more evident, as well as the self-winding capacitance or the leakage inductance. And let's keep in mind that these are parameters that generally don't affect the transformer itself too much, but they will certainly affect you at the board level. So you have to pay closer attention what's going to happen on your system. Not only that, but the transformer itself is affected. Why? Because since we increase the switching frequency, there are going to be more magnetic interactions between windings, among turns of the same winding, and all these magnetic interactions are going to induce losses in the winding. So a magnetic designer will be forced to change the design to avoid having a catastrophic failure in your system. Then we will have to reduce the amount of turns. We will have to increase the amount of insulation in the windings to be able to reduce those capacitances and to be able to reduce the leakage inductance. But not only that, as you may see in this graph, we will have to try to spread the turns far from each other as possible. This way, we are minimizing those magnetic interactions in the winding itself, therefore trying to compensate for the increased switching frequency. Now, at first, one will say, oh, this is great. I am reducing my turns. Therefore, I am going to have a much lower resistance. And yes, that is a valid point. We are going to be reducing the DC resistance. But let's keep in mind that the system doesn't really care about that DC resistance. What the system is going to see is the AC resistance, or better said, the resistance is seen by the system based on the AC signal that we're putting through that transformer. And it is very difficult to predict if the AC resistance, even though we reduce the turns, so it's difficult to predict if it is better or worse than before. Not only that, but since we had to change the internal structure, we will have to go back to our core loss graph. And when we initially thought we were getting 30 milliteslas, if we paid attention to the previous graph, we had to reduce the turns by about half, which means that we are going to increase the flux density on the transformer. In this case, what we will see as we reduce the turns is that we no longer are going to be operating at 30 milliteslas, but somewhere along that line. And just to proceed with our example, since we actually have the turns, then we're literally doubling the flux density. So then now we are operating at 60 milliteslas at a 500 kilohertz. That will give us 500 milliwatts. And when we started off at 100 kilohertz with 200 milliwatts, now we ended up with 500 milliwatts at 500 kilohertz, which means that we are actually getting a hotter component, not a more efficient component. Now, somebody who is acquainted with magnetics may say, wait, you're correct, but right now you're only posting this option where we are sticking with the same core material. What if we just use a better material that has been optimized for 500 kilohertz? And that's a very valid option. Yes, I completely agree with you, but we have to consider different things. First, if you are curious, you may go and check the different materials that are available. And if you look at the best materials at 100 kilohertz, they are going to be better than the best material at 500 kilohertz. So if you compare those two materials, you're still going to realize that the core losses are way better at 100 kilohertz. Now, not only that, but since we had to change the internal structure, you are also going to be increasing cost from the core perspective, from the winding perspective, because even if we use different types of Litz wire or different types of insulation, they all add up. So it's just some food for thought for us to have for future projects. Now, in conclusion, we saw how increasing the frequency of the power supply, ideally we would love to see a smaller part, but we are realizing right now that the benefits may be more evident if we keep the same size of the component for the same power level. So if we keep the same size of the component, we are going to see more benefits as we increase the switching frequency. Why? Because we're going to have more space internally to be able to move those windings around, modifying that structure to have lower AC losses. And yes, we will certainly be able to reduce the size of the component, but it is difficult to predict how small we can go. Now, not only that, but you're also gonna deal with a hotter component. Now, this is the great benefit of increasing the switching frequency, because even if you are maybe dealing with higher losses than before, the advantage is that you will certainly be able to reduce the size. Why? Because we are no longer limited to saturation, because we drop that flux density and we are far from the saturating density. So this is going to allow us to reduce the size of the component. And the other benefits that you will see is that the inductances of the component are going to be more consistent, because you are going to be generally working or operating in the linear magnetic region of the part. The idea is that this presentation fosters communication, fosters questions, and brings up different ideas for future projects. Premier Magnetics certainly appreciates the time that you dedicated to watch this presentation. If you have any questions right now, just go ahead and post them. But if you are not watching this live, you may send us any questions at sales@premiermag.com. And if you want to get in touch with me, Andres Arias, you may contact me through Andres_A@premiermag.com.